Okay, so our second presentation of this session is a gentleman from Germany, Stefan Westphal, University of Göttingen.
Goettingen, right.
Göttingen.
Yeah. So thank you very much for the introduction. My name is Stefan Westphal. I'm working at the University of Göttingen, which is in the exact center of Germany. So we've got basketball in Göttingen. So most of the places in Germany like soccer more, but in our case, Göttingen, we're a big basketball place. So that is Jason Boone, one of our most famous players. Actually, he went to another team, but that's a different story. So you might see that lots of these guys come from America there. Yeah. So let me just now start with basketball. Germany. So that is the German Basketball League has been founded like almost 50 years ago. It started off playing in 1966 with 2 leagues with 10 teams each. And then over the last years it got bigger and bigger, and since 2006 we're having 18 teams and they play against each other. So first this is basketball in Germany. So these are the figures there. You see by now we've got 1.3 million spectators, and you also see that it got more and more, and in this last year there's like quite a jump, right, from 1.16 to 1.32. And in this talk I'm going to show you probably one of the important reasons that happened. Yeah? So even when the capacity of the arenas increased by a lot within that season, the utilization kept up and was even more. So there was quite a jump of 150,000 spectators. Okay, so now what is sports scheduling about in general? So basically it's always about you're giving n teams, you're having n-1 time slots, and now you want to have a schedule for the matches between these teams. This is called a single round robin tournament, and you want in this tournament that every encounter happens exactly once, and the other very important constraint is that exactly one match for every team in each time slot takes place. Yeah? So in one weekend, you do not want to have 2 games. You want to have 1 game a weekend. So this is like the very, very basic properties of a schedule that you need to have. And now you can ask yourself, is that really a hard problem? So just like let these teams play against each other, and when the season is over, it will be done? Actually, it is. So let's see where the problems might be. Let's just assume we have a very small league like this, consisting of 6 teams, and the arcs between these vertices correspond to the games that need to be played. So let's just say these are, so the red colored edges are the games of the first day. So now we can forget about them. And then the next day's games would be these. Third day. So far it looks very easy, and I do not see any application for advanced mathematics here. But, oh yeah, we have a problem. So, when you have a look at one of the teams, let's say the purple one on the left upper side. So this one could play against this team with this dragon, yeah? But then there would be nothing left for the team with the dove at the bottom, yeah? Because he needs to play against both of these teams. So it's just not possible to have the games for the 4th day. Yeah? So you have done like almost half of the days, and you already see you cannot complete the schedule. Yeah? This is a behavior which has been observed like 30 years ago by 2 gentlemen called Rosa and Wallis. Yeah? They found out that for any number n, this can happen, that you do half of the teams, half of the days, and then you do not get a complete schedule anymore. Okay, so it seems like you need to have at least some method to do that. And then the question is, how do they do it? Or how did they do it before? So yeah, that was the problem. Sorry. And then what about the German Basketball League? You want to find here a schedule that fulfills the following requirements as well. First, you need to have a so-called optimal compatibility to the availability of the sports sites. You need to have a minimization of successive home games, so no 2 home games after another, no 2 away games after another. You have media utilization that you need to take care of. Derby matches, which means matches of teams which are located very close to each other, that have to be assigned to a specific day. Then you have some additional wishes for home games at certain days, away games at certain days. And now I want to talk about all these constraints one by one. And so the first thing, and that is the most important one, is the so-called home availability constraints. So I did work for the German Soccer League before, and therefore I thought that was the point I started off from. And the German Soccer League, it works like that. Soccer is very big, so every team has its own stadium, so you do not have to take care about availability of sports sites. It's just there. It has been built only for this purpose. Every weekend there's 40,000 people going there, so that is enough for a stadium to be run efficiently. With basketball, that is different. Basketball is not that big, and therefore it takes place in these multi-purpose arenas. And in these multi-purpose arenas, there's like this one here in Goettingen. Yeah, does not look nice like this, but when there's basketball there, it really looks nice. In these multi-purpose arenas, lots of other things take place as well. For example, here you have like concerts or parties. Yeah, this again, music. Flea markets, yeah, you have flea markets there, even ice skating in the winter. So lots of things happen at these places. And yeah, in the end of the day, these guys want to go there as well to see basketball, right? So this is exactly the same place. Yeah, it's just like very nice. So that means sometimes you cannot go there on every day that you like. The owner of these arenas, they just give you a handful of days and say, here, get along with it. And that was the biggest problem they had, and that was the reason they approached me. This problem is they came up with some schedule, and then they saw, okay, but we do not have the sports site at this weekend, so what shall we do? We have to postpone it somewhere. And then it was not on a nice Friday anymore, or a nice Saturday where you have lots of spectators. It was moved to some Wednesday 3 months later. So what the problem is, on Wednesday it's hard to fill that hall. Yeah, people just do not like to go there on Wednesdays. Therefore, you have got less ticket sales. And the other problem is you have got this unbalanced standings, because in this 3 months in between, you had these two teams. They had just one game less than the others. And therefore, in the standings, it looks like they are worse than they really are. Yeah? So we had, before I started working for them, there was nearly no point in the season where all the games had played the same number of games. That was a problem then. So that was, therefore, this home mobility constraints were the main important thing that need to be addressed. Another thing, which is like the standard constraint in sports scheduling, is that you have successive home or away games. What does that mean? You do not want to have one home game followed by another home game. The reason might be these guys here might cheer up the one weekend. The question is, will they go there the next weekend as well? Or only 2 weeks later, then in the meantime they're just waiting for the next game. But they will not be that motivated if they have that like probably several weeks in a row. Even worse if you have to sit in a bus to go to a different place. 2 away games in a row, even like the hardcore fans do not do that. Probably it's hard to implement family-wise. Yeah, so, okay, then utilization by the media. We have got the German TV channel Sport 1, and it offered 30 broadcasting slots for this season. We've got 34 days, so we wanted to have, on at least within these 30 days, at least one really, really good game. And therefore, we know which games we considered the top games, and though we wanted to distribute them in such a way such that on every of these 30 broadcasting slots, a really good game could be sent. Okay. Minimization of distance on a derby day. So these are the locations of the basketball teams, and now it's on January the 2nd. They wanted to have games such that they do not have to travel that far. Probably that was like, okay, you're after your holidays, and then this is like a nice startup for the new year. On the other way, they thought about probably the players should not have to go that far, when you just had families, celebrations, and the fans also. Yeah. So that was another thing which came up new. Okay, so how does one do a schedule? How did they do it before? First, before you introduce a new concept, you should have a look at what the old concept is good for, right? So therefore, I did that. So there's like a heuristical approach which has been used for at least the last 50 years in German basketball, but it dates back to 18 57 or something, like a seminal work of Kirkman, and it works like that. You have here the encounters of the first day presented like this, and then you derive the encounters of the second day by just turning around the team here in a circle. So now you do this once more, and so you get all these games. You see that the two basic constraints that we had, everyone exactly one game per day, that one is fulfilled here. And if you have an even closer look, you will see that an encounter which happens like this, you will not have that once again when this one is on the other side. So you will have every encounter exactly once. So that is a really very simple scheme, and it's used in many leagues all over the world still. So it was quite successful. So people have like Excel sheets, and then they just have to enter the team into the row, and then they see when they have their home games, and then they see if that is a problem or not. This is Canonical Schedule. It has been presented like to the scientific community 30 years ago by Dominique de Vera in a seminal paper about sports scheduling, and but it's used much longer. Okay, so this is how you can do that, and this is what I did. So I generate first half of the season like this. Actually, when it's about home and away games, you have to add some directions, and it means the game takes place at the side to where the arrow points. Okay, so and then you just have to take care that this one arrow always changes its direction, such it has a nice home and away pattern there. And then you can just you do that, and you get a nice schedule. Yeah, okay. So this is what you do, and then you repeat the same games in the same order, but you just have the arrows pointing to the other direction. So that is the second half of the season. The German Soccer League does it like this. German Basketball League did it like that before. Handball League, I think, as well, yeah. Very, very standard concept. What I did then is I just looked for the best kind of schedule I can get with this method. You see here the whole schedule just depends on the assignment of the teams to the first day, and then the rest you just get for free. Right? So then, of course, if you just change it here, the positions, you get a different schedule. In the end, this gives you a faculty of n different schedules, and this is quite a lot. For 18 teams, I think it's like trillions of possible schedules. But actually, this is the best thing that I got there. I implemented an easy code with GLPK, and then I got the best schedule like this. So the first line is the most interesting one. It means 31 violated availability constraints. So the best thing I can have with this schedule is that 31 times someone wants to enter a stadium which is not there. I asked the guys at the German Basketball League, and they said, like, yeah, these were so the numbers they had before too. So actually, even though they had this scheme and they just did it with Excel, they were quite good with what they did. But of course, they were not able to get better. Okay, so then I thought I'd just take this schedule and then just try to make it somehow better, to do some local search on top. So therefore, I said I would just stick to the home-away assignment. So the days when they play home, the days they will play away, the single teams, I would just stick to that pattern. But I would just change the encounters. That made it somehow better. Okay, it was now 30 seconds, which is still, that was a netbook, so not really a good computer. So very cheap hardware, and so a software like a solver, which did not cost anything as well. 30 seconds, you get a schedule with that, so that is quite reasonable to do, and this is applicable for lots of leagues as well. You know, they sometimes do not have that much money to pay for solvers. That one got a little better here for the derbies. The total distance now was 2,200. And then on top, I took this solution, and then I stick to the encounters, and then I changed the home-away pattern on top. Okay, and the main goal was to get a low number of the violated availability constraints. I could get to 22 this way. Is that good? Can it be better? I didn't know that moment. 120 breaks is far too much. So I took this basic concept, and I tried to fiddle around with it and get something nice. But at this point, I decided to do something else. then I thought, like, so, okay, when I stick to this symmetric plans, what is the best thing that I can get? Now, the problem is when you start the season on one day one, and for a team, the site is not available. Then you start the second part of the season, and the first day is again not available for the same team. Then it's clear that there will always be one violation. Yeah? There is no schedule which can get along with this pattern. So I thought, so what is the problem here about this symmetric plans? And then I came up with a model which only aimed at minimizing that. And I found out that 14 is the minimum number that I have for violations when I stick to the symmetry. And then I started a discussion with the German Basketball League, and they were like, okay, so then what about having non-symmetric plans? So before they did this had a long tradition in doing it the symmetric way. And then, oh yeah, by the way, that is like the distances here are quite nice, 1,000 kilometers, yeah? So you see that is the minimum weight perfect matching, yeah? Or you can guess that it could be one. Actually, it is, yeah? But then we need to try something new because the symmetry did not bring us there. No, we tried to jump very high then. And, at least 14 homoavailability constraints forced us to try asymmetric plans. Okay, what does it mean asymmetry? As I said, you do not have to have the games in the same order, but we wanted to have at least that you have the same number of home and away games in each half, roughly. Not that you have the one half, you have all the home, and then you have all the away games, so it should be somehow balanced. And in each half, you meet exactly once. That was the other thing. So then we set up an integer linear program. Standard thing to do then, you've got a set of teams, set of time slots, variables indicating whether one team should play another team on a certain day or not. And then some variable measuring if there is a break occurring. So then you would just write this down. With these variables, it's a quite natural formulation. You have some objective function here taking care of all these objectives. And then you have got, so I do not want to go through every one of these one by one, lots of constraints which model that. And there is not even more constraints here, broadcasting slots and so on. This all has to be modeled. And then you just start your solver and see what happens. And then nothing happens for quite a long time. Then you get a solution that you don't like. Yeah? And then you think, okay, so this was after 1 hour and 20 minutes. Probably if I wait for 12 hours, I will get something better. Actually, I did not. So that was the thing I ended up with. So the good news is here in the first line. That means there is a schedule such that we get along with the halts that we have. It was kind of sad that this 146 for the breaks, that is quite a lot. I have it here. Probably it's not that easy to see, but it means roughly 8 breaks for each team over the whole season, some even more. When you've got 35 games in total, then that is quite a lot. So this is what they did not want to have. Before they had 48, okay, plus postponing games, but now 146 is much too much. So therefore, I would like to have something which was like as easy as the first models and easy to solve and fast, but that what I wanted to have the solution quality with respect to the first set of constraints here of that model. So I tried to mix these. Yeah. So yeah, that was. So some conclusions in the middle. So what we saw is that was easy to formulate. This is a good thing, but it was not applicable to non-commercial solvers anymore. Okay, then we take something more costly, and but that did not help either. Both of these two solvers had the problem that they somehow got stuck in some suboptimal branch. They run forever. The solution was just not good enough. So this is nothing that you can really go for. So then I did the following thing. I computed starting solutions, and then I injected them into the solver to get somehow better. Then I fixed some variables, and then after several more runs of these IP, I relaxed constraints, fixed some variables over and over again. In between, always this home-away assignments. Then I got a good solution, which looked like this. So first, and this was the good thing here, 0 availability constraints, breaks of 74. This is good. I could somehow prove that you cannot get better than 70, around 70. Home away wishes, okay, you could have gotten a better one there. And again, this total weight perfect matching there. The computation time was quite reasonable. It was 18 minutes, so this is something which is really attractive and can be used there. I cannot hand them over a model and say, like here, when you're lucky, it's done after 1 hour. When you're unlucky, it's done after a week. Yeah, then you have really big models put into IP solvers. You can have a behavior like that. So I wanted to have something which, on my instances, always was fast. So then I can be sure that, or quite sure that it will not happen to take too long at the customer. So yeah, then I was quite lucky, and this guy as well. Yeah. And then when this plan was announced in newspapers and everywhere, and then we got a quite good response then. This one, so this is all in German, but the title from this one is The End of Scheduling Chaos. Math prof helps league out of misery. Okay, whatever. So German's basketball league revolutionizes the schedule thanks to new software. Schedule shall reduce number of postponed. And this is a new dimension. 1.3 million spectators, which is like an increase of 13.35%. So roughly 150,000 spectators more. I think lots of that is because we do not have these games in the middle of the season anymore. Yeah, so we have like no Wednesday games. So Wednesday games, when you go there, it's just lost ticket sales. That's really helped. Probably it's got a little more attractive when you have like a social attention, the media attention. So that was quite good. Everything was fine that way, but that was just I did a solution on my computer. That does not mean that I gave them a product they can work with themselves. And that was the next step then. So if you hand over a standalone software, it has to be easily operable by the project partner. That's the one thing. So you have to have a good graphical user interface. You have to have some interaction with the solver. We see this thing is going nowhere, then you have to stop, or you say, oh, I'm fine with that solution quality. I want to stop here. And of course, it should be capable to solve the problems of the next seasons as well. Yeah, just having a good solution for the one instance does not help. And so we need to have very general formulation of constraints, and a robust and adjustable behavior of the optimizer as well. Their objective might change over the time. And this is the software that we came up with then. A student of mine helped me with the programming here. It's with Java. And so we have here a scenario handling. You can enter data here, and you can have a look at the solution there. So you can enter for the teams, name the attractivity for the TV broadcasting, GPS coordinates for derbies, interesting. The days when games shall take place. When are the places available, when they're not. When shall people want to play at home or away together with some priorities? And you always see the red and then green ones indicate whether this content was fulfilled or not. So then, this looks worse than it is. Actually, not all of them are fulfillable. It's like, I want to have them play against 3 others, so I entered 3 lines. Of course, only one of them can be fulfilled. Okay, and then you've got all the different objectives. You have nice sliders that you can say, I like this one is more important for me than that one, and you can just have your setting for your schedule as you like it. And then you can have a look at the schedule itself. Here, again, this derby day, you see who plays whom. And some more details for the solution quality. The distances driven on the derby day, unattractive home games for single teams, whatever. So lots of things that you can just have a look at. Display of solution quality, as I said, home away patterns here. Then you can see directly. So is there lots of home games after in a row? Yeah. So it's always very important that you have different displays of the same solutions because everybody has a different question that he needs to be answered. Yeah. Okay, and then when you push the play button there, the solver starts. It's got many iterations, and I can always stop one iteration by pushing the stop button. I always see like the current or best objective, bounds, and then when they say, oh, I'm about to 3% optimal, then just push stop, and then they do not have to go deeper. So we did all this with callbacks, where we call it Gurobi standing in the back here as a solver solving that. Okay, so this really helped then. And another view here, you can compare solutions. And that's it. Thank you very much.